This is a video on how to use this table of integrals. If you have an integral which exactly matches one in the table, for example, if I wanted the integral of e to the power of minus 2x dx, I can look in the table and I see that the integral of e to the power of ax is 1 over a times e to the power of ax. So I could look at the table, see that a in this case is minus 2, and apply the formula directly, and say that that integral is 1 over minus 2 times e to the power of minus 2x plus c, which would be equal to minus a half e to the power of minus 2x plus c. And this applies for everything in that table, obviously. So be on the lookout for some of the more awkward looking ones in the middle and right column. So ones like this, the integral of 1 over x squared plus 9, for example. You must be able to recognize this as the integral of 1 over x squared plus 3 squared, so that a is equal to 3. That integral is then, from the table, it's 1 over a, so 1 over 3 times inverse tan of x over 3, plus c, of course. This still works even if the number that's added on to x squared is not a perfect square. So let's say, for example, I had 1 over x squared plus 5 dx. I can say that that's just equal to the integral of 1 over x squared plus the square root of 5 squared dx. So then a is equal to the square root of 5. So that integral would come out to be 1 over the square root of 5 times inverse tan of x over the square root of 5 plus c. The integrals in this table can also be used if instead of x you have some linear function of x. By a linear function of x I mean something like x plus 2 or x plus any number, or something like 5x plus 1, or in a general form you might say something like b times x plus c. So that's what I mean by linear functions of x. So if you have something like that in one of these formulas, you can still integrate it very easily. For example, if I want the integral of cosine of 3x dx, I'll do this one with a substitution just to show you how it works out. So let's say that I let u equal to 3x, then du dx would be equal to 3, du would be equal to 3 dx, or dx would be equal to 1 over 3 du. So I can make a substitution there and say that that is equal to the integral of cosine of u, and dx becomes 1 over 3 du. I can put that 1 over 3 in front and I get 1 over 3 integral of cosine u du. And from the table I can see that the integral of cosine u will be sine of u. Plus c, of course. And the last step would be to undo my substitution, and I get 1 over 3 times the sine of 3x plus c. Now if you look at this, you can see that in the end I just put 3x into the formula where x was before. So cosine x becomes sine x, cosine of 3x becomes sine of 3x times 1/3. And it works the same way for all of the functions in this table. For example, if I look at the formula for tan x, let's say instead of tan x I wanted the integral of tan of 2x plus 5. That would be equal to, well, if it was just x I would have log absolute value secant x, but it's 2x plus 5. So what I'll get is a half, that's from the 2x, times log absolute value secant, and in here I put my 2x plus 5. Now you could do that one with a substitution as well, but there's really no need to make the actual substitution, because you can see that when I differentiate my u, I'll get a 2 for du dx, and so dx will be a half du, and I'll get my half in front, and it'll be the same for all of these. Let's say I want the integral of cosine squared of 10x plus 11. If I look at my table, I have a formula there for cosine squared of x. So all I have to do is put in 10x plus 11 everywhere x appears in that formula, and put a 1 over 10 at the beginning. So that's going to be equal to 1 over 10. And if I go to my formula, I see it's a half times, in the formula it's x, here I'll have 10x plus 11, plus a half, sine, in the formula it says 2x, so here I'll put 2 times 10x plus 11, plus c. So how about this one? The integral of 5 over the square root of 100 minus 2x plus 1 to be squared dx. So pause the video and give this one actually a try. So the first question is, which formula are we looking at here? And it's this one. So if you look at it, that 5 on top can go outside the integral. That 100 is 10 squared, so we're going to have a is equal to 10. And instead of x there, we have 2x plus 1 to be squared. But that's okay. What that means is that we're going to have a 1 over 2 in front of everything. And then, in place of x in that formula, we'll have 2x plus 1. So overall, this one is going to turn out to be, that 5 stays in front. There's my 1 over 2 because of my 2x. Then, the formula tells me that it's inverse sine of x over a. So I will have inverse sine of 2x plus 1 in place of x, and for a I have 10 plus c. So that's it. In the next video we'll see how, if you have different kinds of quadratics below the line in the denominator, you can actually do a thing called completing the square in order to fit it in to one of these formulas. So that's the next video.